Good afternoon to all the participants. Good afternoon to all the participants. It is our privilege to welcome you all to this section 12 of the Faculty Development Program, which brings together experts, academicians, and researchers to deliberate on the emerging trends in deep learning and medical image processing. Our expert for this session is Dr. Priyadarsan Parida. is from the Department of Electronics and Communication Engineering, School of Engineering and Technology, GIET University, Guntur, Odisha. With more than 13 years of academic and research experience, Dr. Parida specialized in computer vision, digital image processing, digital signal processing, and pattern recognition. His research interests include biomedical applications of computer vision, image analysis, intelligent transportation system, and biometrics. He has guided several ongoing research works, published numerous international papers, and also served as a reviewer for reputed journals such as Elsevier and IEEE, as an active member of the multiple professional bodies including IAENG, SDIWC, IRAD, and SCIEI. Dr. Parida brings both depth and diversity in expertise to the LDP. We extend our heartfelt gratitude to our esteemed experts and all the participants for making this program meaningful and impactful. Sir, the session is yours.
Thank you. Am I audible?
Yes,
Am I
sir.
audible?
Yes, sir.
Okay.
It is
Okay.
Yes,
audible.
sir. Yes, sir.
Yes, sir.
Thank you. So I'm just sharing the screen. So anyone can confirm me whether the screen is visible or not. Is the screen visible?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So before going into the topic, that is role of deep learning in diagnosing the diseases using medical images. Prior to that, I'll go for a brief overview of what is deep learning. Then, in our work, how we are utilizing that deep learning for disease diagnosis from medical images, that we will discuss. So, prior to that, what we are using the basics of machine learning. I think 1 decade before it was there. So what we are doing for this particular machine learning is we are using some sort of data, that is the data is available from the images or from various sources. From those data, what we are doing, we are going for checking out the features, what are the features available, and those features we are giving it to the model to make a decision. So when we go for this traditional machine learning, what we are going for, we are going for the typical thing, what we call it as your feature extraction. And in the feature extraction, those features we are giving it to the neural network for different objectives. So whenever we are going for this particular thing, what we are generally going for, we are going for dealing with the handcrafted features. That is the features what we require, we have to select that, and those features we are giving it to the system to train, and accordingly the system must behave. So in that scenario, what is the issue? The issue is how we can select their perfect hand encrypted features. That was one of the challenging tasks. Second thing arising was, that is the curse of dimensionality. That means the if the number of features are much more, then the model may suffer. And again, whatever we are using this trainable system, this trainable system is generally we are talking of a artificial neural network, and the complexities and the size of the neural network, again it was bit slower, and we are not having that type of hardware so that we can get a better result. And when we are talking of again about the encrypted features, the major issue is what, when we talk of a image, because right now whenever we go for to a doctor to a diagnosis, the doctor asks that you go and have this particular radiological graph or like X-ray or MRI. that type of things. But when it is a image, we are having what certain global properties of the image, like we talk of the average gray level, intensity histograms, like that. There are also some local properties of image are there, like we talk of some sorts of lines, textiles, or texture regions, or some sort of shape contours. Those things we have to take into consideration. And when we talk of the handcrafted features, these particular features, these are the features what we are relying on when we are going for this machine learning approach. So you can just see any one or two features we are considering during that time, and that we are giving it whatever features we are extracted, that we are giving it to the neural network, artificial neural network to train. But the issue is which feature is better or which feature is more appropriate for our problem. That particular thing is again difficult. And again, I have told previously that the dimensionality, it also increases from image to image or problem to problem. So when we talk of a neural network, the third component what we are using, that neural network again it is having what, it is just like a human brain, that also we are right now using. But what is that particular thing? Whatever input we give, that input we give it to a neuron, and in the neuron we are having some sort of hidden layers, and based on the human brain processing that particular thing, based on the some words and certain things, that particular thing is processed. I don't want to go for this particular thing because most of us knows what is this. Now I'll go for one particular limitation, that is the parameters. Suppose we are going for, let's say, four neurons. You can see here in the input we are having, let's say, four inputs. Then what is the output? The output we are saying that it is going to be 4 plus 4 plus 4 plus 1. And when it is a image, you can imagine this particular thing, the number of parameters is what? The number of parameters is, you can see it is approximately, it is coming around 230 billion. So that was the most demerit, or you can say the disadvantage of whatever the earlier system was there, if you are using machine learning for directly for going for this processing the images. So what is the issue? Actually the issue is whenever we talk of the image each intensity is having some value. Those values when we consider for lot many things, you can see the parameters gets exponentially increased. And when the parameter gets increased, then there is a issue of what, getting the appropriate hardware, and to do this simulation we require that type of environment. So that is a challenging task for which people were just discarding that particular thing, rather they go forward going for extracting the features, and those features they are giving. Now when we talk of this deep learning, you can see the deep learning right now in our scenario, it is used in almost all the areas. It may be a image classification, it may be a speech recognition. Similarly, when we talk of the biomedical aspect, you can go for your what, cancer cell detection, diabetic reading, that particular thing, media and entertainment field also it is there. The latest one is right now we are going for your what, the security aspect. Whatever this security aspect is shown over here, this is all are biometric, but that biometric is also right now it can be deceptible. So right now the modern trend is what, we can go for some sort using some sort of your quantum based security. That particular thing is right now coming into picture. Apart from that, another field is autonomous fields, where we can go for your automatic traffic management, or you can say smart traffic management. So a lot of applications are there. But when you are talking of this deep learning, what are the things? What makes it deep? So deep learning, what it uses multiple level of feature extractions. So whatever you talk of the deep neural networks, what they do, they tries to extract multiple level of features. So am I audible? Yeah. Anyone can respond me.
Yes, sir,
Yes, sir.
audible,
Audible.
Yes,
sir.
sir.
Audible, sir. Audible, sir.
Okay. When we are talking of this particular deep learning, what it generally provides, I have taken the same features. You can see whatever the initial features I have taken, the same image I have taken. But here, what happens is this network it tries to extract multiple types of features automatically. Instead of using encrypted features, what we are getting three different levels of features. You can see here in the screen I have shown, like you can have some sort of your low level features, some sort of your mid level features, and some sort of your high level features, like you can think of the edge or contour. And when we are giving these features to the trainable system, what happens is the trainable system gets the diverse features. And when it gets the diverse features, then automatically the training is what? Better as compared to your normal machine learning algorithms, what we can see. So when we talk of the basic difference between your machine learning and deep learning, what is that? In machine learning, one step we have to go for, that is the feature extraction. Then we can give it to the artificial neural network, so that it is going to say that whether, like for this example, whether it is a car or not, that output it is going to say us. But when it comes to your deep learning, simply we'll give the image, the feature extraction as well as the classification. That means this entire two tasks, it is going to be covered by the network itself, and it is going to give us the output that whether it is a car or not. So these two tasks it is reduced. So here I have taken classification. It may be some sort of regression, or it may be your segmentation. Anything can be possible. So when it comes to your the deep learning performance, you can just see whenever you are talking of the machine learning, you require what the amount of data goes on, and after certain time, you can just see the performance is what it is stagnant. It is going to be stagnant. Whereas in case of your deep learning, the performance increases on on the rise of the data. And right now, what we are having plenty of data available from various sources. And that also, again, if you'll see, since I think 2014 onwards, when number of networks came into picture like Google Net, AlexNet, BusyNet, those are your patent networks, which is being given by different agencies like Google, Facebook, your Amazon. So what happened is this particular and the parameters, they got increased, and automatically the particular network parameter it reduced. So you can just see when we are having the shallow networks, we are having parameters somewhat around 25.8, but when it came to your resonate, it was reduced to, let's say, 3.57. So that is the particular thing what you can say right now. So in deep learning, the basic thing is about that is your CNN. So it is why it is called as CNN, because here we are adding one operation, that is what we call it as convolution operation. That is, instead of matrix multiplication, we are going to do that particular task. So what is that? Suppose we are going for doing this particular classification task of this particular image. So what you will go for, you have to use a number of layers, and those are the components what we are using in almost in all the networks. So what it does, from this 2D image, every time when you go for your what convolution, you extract features. Then you go for your what some sort of your activation functions. So the activation functions, again, it plays an important role. Then further you go for pulling, extracting that particular features. Then you go for flattening, and here you can see here we are going for in the fully connected network we are going for the same neural network followed by a softmax layer. Now, what are these layers and how it is going to work? Let us try to understand. Suppose I talk of a image, you can see the image. It will be having what if it is a RGB image. You can see it will be having three different channels. Each channel, when we go for multiplying that particular thing or we go for convolution operation, you can just see we are getting a particular value. That is what we call it as your what? That is the convolution output. And combining those convolution output and adding with a bias, what we are getting the resultant output. This matrix is what we call it as a feature in terms of your deep learning. So this particular convolution operation, what it is doing, it is doing the extraction of the features. And what are these kernels? These kernels are applied based on the requirement, what type of kernels we will choose, whether we are going to find the edges or the lines. Based on that only we can decide those kernels. Now, when we talk of this particular thing, let's say for your facial image, or you can say face detection, let's say. So, what we can have multiple layers of convolution. So, when we talk of the multiple layers of convolution, let's say in the first layer of convolution, we'll be getting what low level features. Okay, this low level features will be talking of the what the edges or the dark spots present in the faces. Then we can go for your what, let's say we can go for checking out the mid level features, which may be your what are the eyes, nose. So this is about the second convolution. And in the third level, what we can go for extracting the high level features like what is the structure. So you can see this is the output of your third convolution layer. Along with that, what we are having the convolution, we can have a stride. So what is that stride? Suppose we consider a 7 cross 7 image, okay, and we assume the filter of kernel is let's say 3 cross 3. Then what we'll go for? We'll go for giving the stride. Stride means what? How much cells will process and how much we'll go for. Let's say if we'll go for 7 cross 7 image and if we'll apply a stride of 1, then we'll get a what output of let's say 5 cross 5. Okay. So when we go for 7 cross 7 input and assume 3 cross 3 filter applied with stride 2, then what we'll get? We'll get a output of let's say 3 cross 3. So when it is, let's say 3, stride of 3. So what we can see, we cannot apply that particular stride because what will happen, this particular overlapping, it will be what? It will be missed. So for that reason, what we will go for? We will go for checking out the what? The output size. So what is the output size? The output size is if the image size is n and if the kernel size is f by stride plus 1. That means stride 1, if we'll put for the 7 cross 7 image, so it will give us what? It will give us a size of feature size of 5 cross 5. If stride 2 will take, it will give us a feature size of 3. But when it is stride 3, you can see it is coming around 2.33. So 2.33 cannot be possible in case of your what? In case of your image. We can say. Another thing is what whenever we are going for CNN, the third operation is what we can think of your what is your padding. So whenever you take a image, you can see this image. If you'll go for without padding, what will happen is the first particular cell it will not be processed. But if we go for padding, that is padding the zeros, you can see that all those things are processed properly and accordingly we are getting here the what the features. That means if we'll not use the padding, we'll get a what lesser image. But if we are using the padding, then automatically we will be getting what much more features. Why? Because these features are much more important. So for that reason, another thing that concept that we are utilizing is your what? That is your zero padding. After that convolution and zero padding, that operation, then we are going for pooling, that particular pooling operation. So what is that pooling? Again, we are having number of types of pooling, like we can think of about max pooling, average pooling. So what is that max pooling? Let's say you talk of the max pooling. We can see here that entire image, if I am going for pool size of 2 cross 2, then you can see that entire 2 cross 2 matrix is selected, and from that what we are taking out the maximum value. So if you'll see this particular thing, what is the maximum value? The maximum value is 20. 20 is taken over here. For this cell, what is the maximum value? 30, that is taken over here. If you'll see what is the maximum value is 112, that is taken over here. Similarly, for this, the maximum is 37, it is taken. That means what? The maximum information or maximum intensity variant is taken. If we'll talk of the average pooling, so instead of max pooling, what we'll go for taking the average of all these four cells. So here, what thing we will be getting? We will be getting some sort of here what we can think of averaging operation. So what pooling does, it makes the representation smaller and it is more manageable, and it operates over activation map independently. So you can just see whenever we are talking of or taking a image dimension of, let's say, 24 plus 224 plus 64 features, and if we are going for pooling, then it is reduced to how much? It is reduced to 112 plus 112 plus 64. That means it is going to downsample it. So whenever whatever image we are getting, that image is what it is downsampled over here. Similarly, when you go for the max pooling, you can just see we are taking out the what the max pools, and if it is tried to, then we can go for what checking out this cell, then we are leaving these two cells, again we are taking these cells. So in that way it is moving. But if it is tried one, let's say for this case it is tried one, you can see. So one cell by one cell it is pulling it out, and we are getting a 3 cross 3 pictures. Then after doing those things, convolution, multiple convolution, and max pooling, at the end, what we'll go for flattening those features, because whatever input will give it to the fully connected layer or your artificial neural network, that is your what? That is your flattened input. So what is that flattened input? So whatever features we get from those particular thing, that we flatten it and give it to the what? To the fully connected feed-forward network to do some task. Actually, what is that particular thing? That particular thing is something like you talk of the what? The basic neuron function. That is, whatever input is given, it is multiplied by a word to get the output somewhat like this, which is what we call it as a word. By activation function, that particular thing is checked out. So this activation functions, again, it is having lot of impact over the design convolution neural network. So what is that? One function we can think of here, what sigmoid function, which will be having some sort of values like this, or else we can have your word 10h, or else we can have your word ReLU. So in case of a ReLU, what is the thing? Whatever the zero values are there, that is converted to one. But whatever the negative values in images, sometimes what happens is while extracting the features, some of the features may be what it may be negative. So that consider that particular thing. What we can use instead of ReLU, we can go for your what the leaky ReLU. Some other things are there like yellow function is that yellow function is there. So it depends on what type of design you are going to use. Now come to the architecture. So whatever architectures right now I will be saying, that architecture is what it is, the predefined architectures. So whenever you are giving some input, you can see you'll be getting some sort of your feature maps from the first convolution layer. Then you go for your what pooling. Then again you go for your what convolution to get what the second level of feature maps. Then you'll be getting what the third level of feature maps, and finally those feature maps are what they are flattened and given to the fully connected network. So whatever image we are having, that image is what it is being done from deeper layer. What is that? You can see here we are going for what checking out the what the features. So those features, when we go for taking it out, So it is going to give us the diverse details or diverse information instead of the hand-crafted features what we are using in your machine learning. Now come to the what is the pre-trained networks based on which lot of work has been done in the last 5 to 7 years back. Right now it is nobody is using, but prior to that these things are used. So the basic thing what is that is your linear. It was developed in the year this. So here what thing is there, you can just see here we are going for your what convolution, pooling and nonlinear activation functions. This was the dimension what we are considering in case of the word linear. But what is the advantage? You are using convolution to extract the special features, nonlinearity form, like you can use your tanh or sigma functions over there. But what is the issue? The issue is what when data increase, the computational power increase due to the advancement of additive architecture, but it is not able to tackle that particular thing. Then came the AlexNet, where you can see the dimension was 224 plus 224, and here instead of a single fully connected layer, they are using the two fully connected layer or dense layer, you can say, and they're using the simple ReLU activation function. But what is the issue? The issue is what it was using this support to reduce the overfitting. But the problem is whatever the smaller features are there, they were not captured with large convolution window size of 9 cross 9, because you can see here the convolution window is what it was around 9 cross 9 or 11 cross 11. So for that reason, it was not able to capture that. Then when that particular to address that particular issue, what we are going for the VGGNet came into picture where we are using the kernel size with filters, multiple filters of 3 plus 3.
ହଉ ଆଉ ନାଇଁ ମୁଁ କହିଲି କାଡେ କଥା
And in that way, this particular thing was going on. And here you can see again the thing was developed for your ImageNet. But what is that? The issue is what when you are using multiple 3 plus 3 kernels, the issue was you are having high computational complexity. For that particular thing, what is the thing? Inception came into picture. You can see Inception, the architecture was much more complex. You can see the architecture, it is much more complex as compared to your what, as compared to your previous one. But what they gone for, they gone for your what, this particular architecture, we call it as a what, we go for multiple skip connections over here. So in that case, what is the thing? You are having what you are using one plus one convolution. Okay, but the issue over here is you are facing your network is facing with your what struggling with your vanishing gradient issue. Then comes your what the residual connection. You can just see that you are using a what when this particular to avoid that particular vanishing gradient issue. What we are going for? You are going for checking out a skip connection, and whatever features were lost over here, that may be what compensated by this particular skip connection, or you can say residual connections. So this particular residual connections were introduced in your ResNet. That is, lot of variety came into picture. That is ResNet 50, ResNet 18, ResNet 101. That particular thing came into picture. But what is that? It offers fewer parameters, provides in-depth features at different levels. But the issue is what when it came to your what batch normalization, or you are going to what adding this skip connection, the complexity of the architecture it increased or manifold much. Now, how we can use that particular thing when we talk of the medical images? Is my screen visible right now? Yeah. Anyone can respond. Hello. Is it visible?
Yes, sir.
Okay. Okay. When you talk of this medical images, I'll go for one or two particular area where we have worked. Not all. I'll be. It will be not possible for me within the limited time to go for this. Okay, one of the area is what identifying the brain tumor or identifying the brain-related diseases, how that particular thing is happening. Let us try to understand that particular thing. So, whenever we talk of the brain tumors, everyone are fascinated about what the brain tumors. Generally, brain tumor is not a single one, but it yeah. Anyone is asking any query? Any query is there? Any query is there? No. Okay. So, whenever you talk of this particular brain tumors, so this brain tumor you can just see here. This brain tumor is not a single tissue. Rather, here we are having got multiple things present as what we call it as entirely as brain tumor. That means you are having got basically the core structure of the tumor is you are having your what the tumor core and you are having your what the non-enhancing tumor. That means within the tumor core, some let's say this particular portion is your what tumor core. These are the what non-enhancing part. Along with that, you are having some sort of your edema. So these green one, these are called as your what those are your edema. So what you have to just check it out that your tumor is not a single thing that is consisting of three different components. And from the growth of this particular tumor core or whole tumor, this enhancing tumor, then only we can identify that what whether that particular tumor is going to be fatal for that particular person or not. So using that concept, what we have observed that when we have gone for using those inception V2 or we have gone for what the other patent networks, what we have observed is whenever we are going for this brain tumor, okay, you can just see here this particular thing that is the tumor part. It is available in form of in the data set. It is available in form of your this clusters. Now, when we applied the pre-trained network, that is inception P2 for this particular tumor extraction, you can see these pre-trained networks they suffer a lot. You can see here they were identifying this entire marked blue mark region. They are all are marked as a what the tumor regions. But when we changed some of the networks then with the inception bit, we added 16 in the added layers. Then what we have observed that what the tumor parties were identified. So now the question is that what we have done. So if you have gone for this particular image, yeah, any queries there? Yes, any queries there?
Same to you, sir.
Hello.
No, no queries, sir.
Okay, okay, okay. Okay, what we have done, if you'll see this particular thing, that we have taken the input image, then what we have done, we have gone for augmentation because whatever image we have considered initially, the images slides are available as very less. So for that reason, we have gone for augmentation. Then what we have gone for, we have gone for using the pre-trained networks. We have taken the pre-trained networks and we have modified the last 16 layers. That is, we have added the 16 layered segment over here. So when we have added it, that particular thing, then what we found that uh, this particular tumor regions they are much more highlighted. But apart from the tumor region, you can just see here these some small portions they are also identified as tumor, but which are not. So what we have done some sort of your what intelligent analysis that whatever the whole tumor is there, that whole tumor is what it is having much higher area. So what we have gone for, we have gone for some sort of your area filtering, that is a morphological operation. So what that particular gave us, that particular thing gave us what? It gave us a mask where you can see only the tumor is extracted, whereas the other parts, smaller regions, they are disbanded. Now, when that particular thing happened, what we extracted? We have extracted the whole tumor. Once we have got the whole tumor, then from that whole tumor, what we have to go for? We have to go for the what? Extracting the what? The tumor core, tumor edema, enhancing tumor, all those things. So what we have gone for? There we have gone for some sort of your what you can say unsupervised approach over here. Why? Because this particular thing is what that particular thing is. Yeah, am I audible? Am I
Yes,
audible?
sir.
Yes, sir.
Sir, there is a
Okay.
lot of
Uh,
noise in your background.
in the background, lot of noise is there.
Yes, sir.
Okay. Okay. I hope right now it is okay. Fine.
Yes, sir. Yes, sir. There is more noise in background right now.
Is my voice audible right now?
Yes, sir. Yes, sir.
Okay. 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 So in that case, what happened is when we gone for this particular whole tumor extraction, then we have gone for enhancing that particular whole tumor part. Later on, what we have gone for? We have gone for using the fuzzy Siemens clustering to segregate the what the different particular tumor regions like the whole tumor, the tumor core, this edema, enhancing regions. So those things, what we have gone for, we have gone for extracting that particular thing using the clustering technique. So this particular approach is saying that what a single CNN also it is not able to take care of all those things. Rather, what we can go for, we can say that we can use some sort of supervised along with your what unsupervised approach. And this particular thing, what we have added, that particular thing I have shown it over here. You can just see here that whenever you are having the input image, you can see in we have given it to resonate V2, and apart from that, what we have gone for, we have gone for adding the 16 layers. So these 16 layers, what we have carefully chosen so that we are able to get a better result as compared to your inception V2. So this was our first experimentation with the customized CNN. So here what we have gone for, we have gone for some modification of the inception V2 uh, layer network. Okay, and when we have gone for this whole tumor enhancement, what we have gone for, we have taken the whole tumor region, then we have taken these steps for image processing, that is what are the input parameters, then you have partitioned into different regions, and then you have gone for your mapping, and finally we have got the what the enhanced image. So this is what the whole tumor what is enhanced, but what is there you can see here, what is there shown or what is extracted, you can see here there is no chance of getting the what the tumor core and edema, all those things. But if you see here, there are what some sort of your what texture which is uh, enabling us to get the better result of those tumor sub segregations. So when you gone for this particular thing, you can see here that particular enhanced whole tumor. We have got this type of clusters. These clusters we have got, and based on that, what we have got the what this segmentation. And here you can just see the segmentation results, and those segmentation results are what we have obtained for the from the whole tumor to the entire tumor subregion segregation. Now, the second thing is what whatever we have got, whether it is correct or not, or whatever we have got, whether it is good or bad. So for that reason, what we have gone for, we have gone for checking out this particular thing with various performance metrics. What is the performance metrics we have considered? The performance metrics we have considered for what the whole tumor, that is the accuracy we have considered. So accuracy of the whole tumor we have got it as how much? We have got it as 99%. So somebody will say that okay, accuracy you are getting 99 means there is no further work has to be done. But for case of segmentation, the accuracy is not the proper metric. You can think of what the actual overlap with your ground truth. So there you have to go for what another part, that is what we call it as your what, that is the dice coefficient. So here you can see, observe the dice coefficients what we have gone, the dice coefficients it got as the whole tumor as your what, it is 89%. So not only that particular thing, rather when we compared it with the what, the edema and the tumor core, it was coming around somewhat around 86 to 84%. So from that we have checked that for BRAT's 2017 dataset, we have got this value. Again, we have compared it with the BRAT's 2020 data. There also we are getting accuracy somewhere around this, but accuracy is not speaking the entire thing or entire story of the what this tumor segregation, rather the dice coefficient. So that dice coefficient, it here we got the value of somewhat around 90% for the whole tumor. And whatever the edema and tumor core, it came somewhere around 86 and 85%. So that particular thing told us that there is much chance of improvement in this particular segment. So this particular paper, I think it was published in the year 2023. Later on, what we gone for, we have gone for what, checking out that same thing, experimentation with resonate. Why? Because inception V3 it was not having that residual connection, but resonate it is having residual connection. So what we have done for gone for, we have gone for using this resonate. So when we have gone for this resonate, you can see here what we have taken. We have taken a hybrid deep neural network. That means what we have done, this resonate 101 we have taken as it is, and along with that what we have added, the last 10 12 layers we have replaced it. These 12 layers, it was completely designed by us and it was replaced. So this particular hybrid deep neural networks is referring to this entire network. And when we have gone for this particular thing, then what we have observed that we have got a result slightly better than the previous one. But still, what is the issue? The issue is still we are getting some sort of issues like some regions which are not having tumor, they are being given by the network that it was having tumor. So this time also we have gone for some sort of morphological operation for extraction of the uh, particular whole tumor, and then we have gone for checking out this particular whole tumor sub-segregation, that is into tumor core, edema, and your enhancing tumors. So here, instead of going for the basic fuzzy Siemens clustering, here we have gone for CLA clustering. That is using center of mass clustering method we have gone for. So here, this particular work is again a combination of supervised as well as unsupervised approach. So, sorry, K-means clustering. So here, what thing we have done? We have gone for your what? First, we have gone for taking the whole tumor by using the what K-means clustering. We have segregated the edema and the tumor core. So, how we have gone that done that particular thing? We have gone taken the what, the mask of the whole tumor. Then we have changed it to a color space, that is your lab color space. Then after that, what we have gone for applying this k-means clustering over the lab color space. So what it segregated the tumor core and edema for us. But that particular thing, it is having issue that the entire thing we are not able to get, because there are three things are there: whole tumor, enhancing core, then we are having the edema. The entire thing you are not able to find out. So for that particular thing, what we have gone for, we have gone for applying another clustering technique, which is called as your center of mass methods. That is your local center of mass clustering. So that center of mass clustering, what we are going for checking out the, prior to that we have gone for enhancing that particular whole tumor. Then whatever enhanced tumor you have got, we have gone for computation of this local center of mass. Then based on this center of mass, we have got the tumor segregation. So what type of segregations we have got? We have got the segregation somewhat like this. You can see we have got the segregation somewhat like this by using this LCM methods, that is local center of mass method. And what we have got, this particular thing, we have tested it for two benchmark data sets like that's 2017 and 2020. And what we have obtained the accuracy again, it is 99%. But when it comes to your what, the dice, we have got it as what, 84% for this. That's 2070 and 84.88 for case of your what, Brass 2020. So here what we have observed that what this same particular thing, if we are going for what combination of supervised and unsupervised, along with whatever supervised approach network is there, if you are going for small modifications, that is not going to help us out in extracting this particular task. After that, what we have gone for, we have gone for checking out what are the different types of tumors. So whenever we talk of the brain tumors, you can see there are different views of our MRI scans. Like we can have your what, axial view, coronal view, and sagittal view. Along with that, you can see there are different class of tumors. Like brain tumor is not a single tumor; it is having a different class. Like you are having meningioma as one class, glioma is another class, and pituitary tumor. You can just see, you cannot look at this tumor. The tumor is very small. That is your what, pituitary tumor. You can see it is nearly located nearly the what, the pituitary gland. This particular region it is located, and it is very small in nature. So that particular thing makes the task more challenging. So what we have understood that what, only segregation of the tumor that may not be enough. So what we have to go for, we have to go for what, checking out the what, the pituitary tumor. And for that particular thing, one particular typical data set came into picture during that time, I think around 2023 or 22. That is the fixture data set. So in that data set, what is the data distribution? The data distribution is around, it was having 3064 slides, but out of that you can see the class imbalance was what, it was having more number of, you can see the glioma, whereas the pituitary tumors are the second highest, and the meningioma is what, it is the least one, that is 708. So there is a high class imbalance. So we have taken those, that problem, that what, let us go for checking it out, that how we can identify different types of tumors or extract different type of tumors, along with whether we are able to identify their classes like meningioma, glioma, or pituitary tumors. That particular thing, for that particular thing, we have gone for one particular architecture. I think this particular paper, it came around the year 2023, where two tasks are performed simultaneously. Uh, One is your what, one is your segmentation task, and the second one is your what, that is your classification task. So two particular typical tasks, what we have gone for that particular time, that is, first we will identify the tumor, then we will go for your what, checking out that what is the type of tumor. That means first location of the tumor, localizing of the tumor has to be done, then we will go for checking out the what type of tumor it is. So you will see the architecture, what we have taken the input image, that is MRI scans, and we have segregated into three different parts, that is training, validation, and testing. And here what we have used residual unit. We have considered the unit for segmentation. Now once whatever segmentation result we have got, this is the segmentation result. So this segmentation result is what we are adding the tumor ground truths what we have obtained over that particular segmentation result. So what we have got a fused image, that is the segmentation mask which is generated along with the original tumor. Then that particular thing we have added or given it to a what? We have given it to yellow V2 version, for, which is again a Britain network. We have performed transfer learning, and that particular thing give us the output as what, whether that particular scan is whether glioma or meningioma or pituitary tumor. That means what, we are able to identify that where is the tumor. That tumor location is got over here. Once that tumor location is identified, then further we are able to identify that whether that particular tumor is belonging to which type of tumor or which category of tumor. So what that resonate you there's net 18 plus unit architecture. You can see the architecture is somewhat U-shaped in nature, you can see here. So what is that, whatever image we have taken, the image is of, let's say, 240 plus 360, and that we have gone for what, giving to multiple convolution layer and ReLU layer, you can just see here. And here we are using the stride of 2. So what it does, it downsamples the data. And here, whatever we are using the skip connections, what it is doing, it is going for whatever the downsample, during downsample, whatever features are lost, those features are what? Those features are recovered over here by these skip connections. So that what is there, after downsampling, whatever features we are getting, those are again given to the decoder blocks to go for your what, upsampling. So here the upsampling process is going on, so that whatever input we give, we are getting the output as what, a image of 240 cross 360 cross 2. That is two pluses, only a black or a white it is coming. That white is considered as your what, that is the tumor. So that is the what, the segmentation task. In case of your yellow version 2 transfer learning, what we have gone for, we have gone for taking out whatever we have identified the typical uh, segmented mask that we have added or fused with the original image. So here you can see, this is no more the original image. The original image is fused with the what, the tumor mask. Okay, because that particular thing is giving more information to the network to identify the various types of tumor. Because whatever you see, the tumor is having variety of sizes. Like you can say meningioma, it is having a larger size, whereas the pituitary tumor is having very small size. Like meningioma, you can say it is somewhat around 2 cm to 3 cm, but whereas for meningioma, it is available in terms of few millimeters, like 6 millimeters or 7 millimeters. Okay, so that was the major issue for what you can think of the what, the tumor classifications. And this yellow V2 network, it was performing well for this input, because this input is our extracted mask fused with the original image. So when you give that particular thing, it is capable of identifying the what, it is capable of identifying the results. So what results we have obtained during that particular process, you can see we have got the results somewhat like this, and it is applicable. We have checked out that it is applicable for all views of MRI scans. It may be coronal, or it may be sagittal, or it may be longitudinal view. All views, it was working well. So when it comes to your what, the classification, you can see here the classification, we can just check it out by the usage of your word, that is your confusion matrix. So confusion matrix, it better speaks much more about the what, the classifications. And you can see here what is the output. The output is what you can see, the gliomas, meningiomas, and pituitary, it was coming somewhat around here what, for every class gliomas, it was 100%, nearly 100% it was detected. The second one is your what, that is the pituitary tumor, that is around 90% it is uh, getting here what, better detection. Okay, and for pituitary tumor, you can see that particular thing we are getting less, much more less. And whatever this particular work we have gone, because as this is a new concept of what achieving both segmentation and classification, that particular thing was accepted during 2023 in one of the reputed, that is Biocybernetics and Biomedical Engineering journal, for this particular task. And what type of performance we have got in terms of objective analysis, we have got or we have achieved the segmentation performance of around dice around 90.11. That is the value what we have achieved. Similarly, when it comes to your classification, you can see here the classification of this particular approach, what it achieved. The F1 score you can consider, because accuracy is not always the correct score for your what classification also. We can think of what considering the precision and recall. So for that reason, we'll consider the F1 measure. So F1 measure, it is getting somewhat around for meningioma, it is somewhat around your 91.7, whereas for glioma it is 95.5, and for pituitary tumor it is 96.9, and on an average it is giving us the accuracy somewhere around 94.7. So you can easily understand that as this particular method no one has done, whatever we have compared with the individual methods. Like these people, they have only worked with classifications, and these people, they have only worked with the segmentation. But whatever we have worked on both combinedly, segmentation as well as classification. So in that scenario, this particular approach, it got identified by the reviewers. So once we have gone for that particular thing, till now whatever we have used the what, the pre-trained network, the concept of your what, the unit, that is again a pre-trained network, also your yellow v2, that is again a what, pre-trained network. So using those pre-trained network concepts, what we are going for getting the result. But that may not be the best one. Why? Because the complexity, it was much more higher using this pre-trained network. So what we have gone for, we have gone for certain things like designing our own network. So how we started designing our own networks? We have started for checking out that same task by using our own network with fewer number of layers. So if you try to recall what is the number of layers in unit, you can see here we are using somewhere around what, more than
Sir, you are not audible.
same thing by our custom layer network for your segmentation, that we named it as a 20 layer network, that is MTA, multi-tumor analyzer 20, that is for segmentation. Once that particular segmentation was done, so what we have got the tumor mask. So whatever tumor mask we have got, that tumor mask, we have again fused it with the what, with the original images. Okay, then what we have gone for, we have gone for designing a 55 layer network for your what, for your classification task. So whatever the classification task is there, that classification task, it was again doing the same job of your what, finding out the what, the meningioma or glioma or pituitary tumor. Am I audible? Yeah, anyone?
Yes, sir.
Okay, 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 thank you. So this same task, when we have gone for doing this, you can see here how we have designed this particular layer. So what we have taken to the convolution layer. Okay, then dash normalization layer, liquid yellow layer. So instead of normal yellow, what we have gone for, we have gone for liquid yellow layer, and then it is followed by a max filling layer. So here you can see one particular thing is what we can say. This is what one encoded of what you can say. And here from this particular MRI image size, what we have considered, that is 227 plus 227 plus 1, because what we require that what, that particular image dimension should be limited within that, because if it is more than that, again it will be difficult for us to work, for our hardware to support that particular training and all those things. So what we have gone for, we have gone for here three encoder blocks. You can see here we have gone for only three encoder blocks. And after that, what we have gone for, we have gone for after downsampling, whatever we have got, we have gone for only one decoder block, that is our transpose convolution layer, that is 2D transpose convolution layer. Then we have used a single convolution layer. Then we have gone forward your gas normalization and followed by softmax and pixel classification layer. So you can see here that is the output what we are getting after this particular layer. So here whatever we have taken this particular thing, you can see we have got the same result, almost the same result, or even better than the written networks what we have used. So what is that particular thing? You will see this particular thing. This network is what you can see. This network is somewhat like this, and whatever we have taken the classification network, the classification network is this network. So you can see this classification network. It is a 55 layer network which is taking the inputs as the what the fused image of your whatever you have got the segmentation output along with the original image. So here the input is what, it is a fused image what we are giving, and it is a 55 layer own custom network what we have considered. So here you can see we have used the convolution layers, max pooling, fully connected, dash normalization, and GAP, global average pooling layer. So these layers combinedly we have used, and what we have gone for using a fully connected layer, single fully connected layer over here, and there we are getting the result. So what result we have got, you can see here the overall performance for this MTA 20, that is for segmentation performance, what we have got the dice coefficient of around 88%. You can see the dice coefficient what we have got is around 88%. That is the better one what we have achieved. Similarly, when it comes to your what MTA 55 deep neural network, you can see we have got the F1 score around somewhere around the meningitis 99.37, and this glioma we have got it as 99.83, and for pituitary tumor we have got the value as 99.77. So that means it is demonstrating that whatever performance we have got using pre-trained network, if we are going to design our own network, therefore we will be getting a better performance. And in terms of the network parameters or complexity, that complexity is going to be reduced. So that is the main motto behind this particular work what we have done. Any queries related to this? Any queries or any questions so far?
Sir, excuse me, sir.
Yeah, yeah,
Sir,
please.
sir, you told about the fusion of the normal images along with the segmented images.
Yes.
So exactly in programmatically how it is being done means that image is added with the
Yeah,
within the
we have simply gone for addition. There is a option of what adding two images, like one image. If it is let's say if whatever result we are getting, this is here. This result, let's say we are getting the result to be what let's say black and white. So your white pixels, it will be considered as what, let's say 255 intensity value, and the black pixels here it is considered as, let's say, 0. So when it is added with this particular thing, so 0 will be having no significance. You can see if I am going to add this particular thing over here, this zero, wherever there is zero, that zero is added with some intensity value, that is not having to any significant impact. But when it comes to your what 255, that 255 is going to check, put the major impact. So that 255 region, what it is, when it is added, what happens is what, in this particular image we are not able to locate the what the tumor, whole tumor properly. But when it is added, you can see here the resultant. When it is here image fusion result we are getting, the resultant image is what, it is much more clear. So whenever it is much more clear, then it is like we people see and we understand this particular thing. Similarly, if the network will neural network is what, those are your learning things. So if we can learn the things better way, similarly the network has learned this particular color highlighting in a better way, and in that way it is giving us better result.
In the data set, 25, let's say 25 images are there, and we are getting
Yeah.
25 segmented images. So individual image will be added with the its corresponding segmented image. So
Yes,
finally
yes.
also we'll be getting 25.
Yes, yes, yes. Whatever dataset images there for this fixed dataset, I think it was 3064 images we have considered. That same number of images we have added with the whatever we have got the segmentation mask, so that when it was added or overlaid, so you can see there is a change in the color. So there is, when there is a change in the color, you can see here the gray intensity values, they are not easily recognizable by the what, by the neural network. But when the color information is there and some sort of highlighting is there, it was easily picked up by the, this information was easily picked up by the neural network. For that reason, it gave us good result.
Thank you, sir, for the clarification.
Yeah, thank you. Any other queries? Any other queries? No. Okay.
Any other
So,
queries? Okay.
okay.
Thank you, sir.
So, so that was the part of the brain tumor. So how we can extend that same thing into other domains, like other medical imaging domains? One is what we can think of here, what, the retinal image. So most people think of what, going for a retinal disease analysis or retinal disease classification. So that particular thing we extended it to this retinal disease classification. So you can see here one of the work we have done, and very recently, I think in the month of August only, July or August, it was published. So here, what we have done, we have used the concept of this same thing of our custom neural network. So this custom neural network, whatever we have considered here, we have named it as the deep retina net. So what is that particular thing? What we have gone for? We have gone for checking out the what, the blood vessels of the retina, along with the diseases identification using those blood vessels. So that particular experimentation we have tried, and that when we tried that particular thing, then we have got the different disease classification accurately. It is not only used for one or two; it was tested against multiple data sets. So, what is the architecture? You can see this is the deep architecture what we have gone for. So here we have gone for two architectures. One is your segmentation architecture, that was having here what, residual control net, okay, architecture and AED net. And here we are using one classification architecture, that is your what, that is STD net. So retisegnet architecture, whatever we are using this segmentation architecture, it is having two parts. You can see here the network, it was completely designed by us, and this layer, you can see this layer is not your simple network. It is one of, you can say it is looking complex network, but it is using the simple blocks like whatever I have told, the 2D convolution layer, all those things. But here, what thing you have used, instead of 2D convolution, you have used here what, autologous convolution. So that is again another modification of the what, 2D convolution layer. And here, what you have used the autologous convolution to get the result. So here, whatever the strategy we have followed, after designing, so we have got the what first the vessels. So here what we have obtained the vessels over here. That is the reticular output. Those vessels again it was added or fused, and when it was fused and it is given to a classifier, this classifier is again completely designed by us. So when it was used, what we have got the outputs that what are the disease. Okay, here I have taken typically four diseases, but we have tested it on multiple data sets. And here one thing we have gone for adding the LSTM blocks, that is long short term memory network blocks over here. So you can see here how many, how much images types or what are the image types we have considered for checking out this particular data set. So this data set is validated for more than six data sets, out of which almost all are popular one. Those who are working with this particular um, fundus image, they can identify. And the major limitation in this work is what we don't get much more image. We get very less images. And what we are getting the output in terms of the segmentation results. So whatever the segmentation results we are getting initially, you can see here we are getting the segmentation results in terms of your what the vessels. So once we have got the vessels, then what we have taken that whether that vessels are actually located in the fundus images in this way or not. So what we have seen that okay, whatever the you can see the optic disc part, that the optic disc part is what it is visible. So from that we analyze that okay, whatever we have done the segmentation, that segmentation is okay. And also we have validated with the ground truth. And for classification task, what we have gone for checking it the classification with whatever the classification data sets are available. Based on that, we have gone for the classifications. Like in one data set, we are having the what uh, these three classes like diabetic retinopathy, MH, and the normal. In another data set, we have the what the cataract and normal. We have checked those things whether our classification network is performing well on every data set or not. And similarly, we have taken the other data set where there are four classes. That is, we are having your AMD, diabetic retinopathy, glaucoma, and normal. So all those things were what it was pretty much verified that okay, it is working well. And that particular thing again we have compared with what numerous approaches you can just see for different data sets we have compared. And what we have obtained is we can say that this dice coefficient for the vessels, what we have obtained is it was the maximum of all the data sets. And these are all recent techniques what we have compared. Similarly, for classification, we have checked the word the F1 score, because I have told that the best thing for classification you can use is the F1 square. And here, almost in the five data set, we have got 99, uh, whereas in case of your RFMD or ODI, we have got somewhat around 95% accurate in the F1 score. So that told us that okay, what things were we have done, it is okay. And that particular thing we have checked it out, that how further we can go for designing the custom neural network for every task. And these are the references what we have what I have used for preparation of this slide. And some of them are my own, some of them are others. Okay, I think I am over up to this. Any other queries are there, it is most welcome.
Any queries?
Any queries are there?
I think there is no query. Thank you, sir. On behalf of the organizing committee and all the participants of this faculty development program, I extend our sincere gratitude to Dr. Priyadarsan Parida for delivering such an insightful session today. Your talk on the role of deep learning in diagnosis disease using medical image has truly enriched our understanding of how advanced computational methods can revolutionize the healthcare domain. The depth of our expertise in computer vision, image processing, and biomedical application was evident throughout the session, and your valuable insights have provided new preservative for both research and practical application. We deeply appreciate the timing and effort you invested in sharing your knowledge and experience with us. Your session has certainly inspired participants to explore innovative research in deep learning and medical image processing. Thank you once again, Dr. Parida, for being a part of this FPP and making it more meaningful and impactful. Thank you.
Thank you. Thank you all. I think I will leave. Okay.
Our next session will start in just 5 minutes.
ଏକୋଇଶ ବାଇଶ 22 23 ଅଛି।
Hello, sir. Am
Yes,
I
madam.
audible?
We'll start now.
Okay, sir. Okay.
Good evening to all the participants. It is my privilege to introduce our esteemed speaker for this session of Faculty Development Program. We have with us Dr. Rajitha B., an accomplished academician and researcher currently serving at the Motilal Nehru National Institute of Technology, Prayagraj. Dr. Rajitha has an illustrious academic journey. She completed her B.Tech in Computer Science and Information Technology from Kamala Institute of Technology and Science, Telangana. Pursued her Master of Engineering in Computer Science and Engineering from Karunana University, Tamil Nadu, and earned her PhD from MNNIT, Allahabad. With over 14 years of teaching and research experience, Dr. Rajitha has made notable contributions in diverse areas including image processing, medical image processing, multimedia processing, machine learning in computer vision, deep learning, and quantum machine learning. She has taught a wide range of courses such as artificial intelligence, data science concepts and methodologies, software engineering, image processing, and introduction to AI/ML. Her expertise and passion for teaching and matched by her strong research credentials. Dr. Rajitha is also a senior member of IEEE and a member of ACM, reflecting her active engagement with the global research community. We are truly honored to have her with us, and we look forward for gaining valuable knowledge and perspective to her session. The session is your man.
Thank you, Dr. Abhishek Mishra, for your kind welcome. Sir, should I start my presentation then, the talk?
Yes, ma'am.
Okay. So I am actually sharing my screen. Let me know if it is visible or not. Is my screen visible now?
Yes, ma'am.
Okay. Okay. Thank you so much for your kind invitation in your university for this online workshop. And myself, Dr. Rajita, as Abhishek sir has introduced me, I'm working as an associate professor at MNNIT Allahabad since 2012. And my main research interests include image classification, computer vision, medical imaging, and right now I've just started my research in quantum processing as well. So today's my topic would be in the future of medical image classification using the deep learning models and the how we can deploy or how we can have the quantums as well for deploying the classification models in real time. So let us focus on our topic. And in today's topic, today's talk, I would be talking about the few basic things here, like what is medical imaging and what is an image, types of an image, types and images, what type of images do we have in real time applications. Then we will be looking at importance of medical image classification, which I'm actually taking into a short notation as MIC. I'll be calling as MIC now my slides, medical image classification. And then we'll be looking also at what are the current challenges, and then we'll be looking at motivation of using deep learning, followed by what all methods we have adapted in deep learning in medical image classification using the deep learning models. Then followed by, I'll also be talking about few challenges what are left out even with deep learning models, wherein the rise of quantum might help in doing the better classification of medical images for real time adaptability. Okay, now let's look at the basic. What is an image? Now, as we all know, an image is like a picture or pictorial representation where human can look at any description or any natural scene. Now, if I talk about a digitized image, the natural scene or the captured image should be stored in a machine in the form of digitally. So a digital image can be defined in terms of mathematically as a two-dimensional function noted as f of x comma y, where x and y where x and y are the spatial coordinates, and we will have an amplitude f at a pair of coordinates xy, which is called in image is to be as an intensity of that level. And these intensities are having the property of discrete quantities. They are not continuous because you are having an image which is having a pixel, and pixel is in the form of an numerical value, so it is always an discrete entity. So now that pixel we are calling as an pixel. Now pixel is image we represent the image in the form of an like digitized image which we are storing in an particular device. So how do we capture that image? As we know, we will be having a camera which will be projected on some object through the light illumination whatever we have the energy source. That a real-time object is captured through this device into a digitized photograph. Now, this digitized photograph is stored in your machine in this form, like it is shown in the last one, which looks like a 2D matrix. A certain rows and columns followed with an every pixel cell. Now, this every cell is represented as an pixel, right? Now this pixel can be of holding different values due to which your color gets generated in your image. Now basically the basic type of image is an 2D matrix which we are storing to capture the original object representation. Now, this particular pixel or the image is taken in from the device, a camera. Now, that camera will be taking a spectrum range of visible light spectrum from 400 nanometers to 8750 nanometers. So, the image will be generated within this particular range. Now every device should be capable, every device what we are using for digital image generation, it uses this particular range itself. Now based on, if you can see this the screen which I'm showing right now, if you look at the different spectrum ranges, now depending on that frequency level, the type of image what we what gets generated is different. Like some gamma rays can produce different type of imaging, x-rays will produce different type of imaging, ultraviolet rays develop different type of imaging, radio waves and infrared rays will produce different type of imaging. That means we will be having different types of devices to capture different forms of images in real time. Now every device is not the same. Now, categorization is done according to the what wavelength spectrum it can hold and what type of images it can create or capture. Now, depending on which we have wide varieties of images, which of them are certain examples are given here. Few of them is the gamma rays can produce these type of images as I'm showing on the screen. Similarly, the X-ray spectrum can produce the X-ray of an human, of an organ, or like an digital scan of an X-ray, like we do at the airports, right? So we have a different spectrum for different type of application. Now, X-rays are used for different form of applications. Gamma rays are used for different form of applications, and ultraviolet are used for different sorts of applications, and visible light spectrum is used for different type of application. So like this, we have n number of images which are generated in real time. So the radio waves can be used to generate your MRI images. Infrared rays can be used to generate the thermal images, and similarly synthetical images can be generated using the microwaves, right? So like this, we have wide sets of imaging, and which can be captured or which are captured for different sets of analysis in real time, or the observations which we can be doing in real time. So similarly, ultrasonic imaging is also one such category, wherein we'll try to um, look at the internal organic function of an body, of an human body. As you can see from all these slides, like around 3 to 4 slides, you can see that all the data that we want to capture, which is not visible by a normal human eye, can be captured with different sets of rays. Now, you by using different sets of devices which can generate those waves, you can generate different sorts of images. Now, our topic is more specific towards the medical imaging. Now, I'll be focusing only on medical domain, not the other real-time computer vision and other types of applications. So, today's topic is specific to imaging. So, we will be looking only at medical domain applications. Now, if I try to store an image in a machine, as we have already seen that the image is stored in the form of f of x, x comma y in a 2D matrix. Now, I told you that it will be stored in the form of a matrix. Now, how does it store? How does it really impact in the memory? If you can see the particular slide which I'm presently presenting, here you can see that the image what I'm going to hold here is of size 2724 with 2 through 2336. Right now, these many is total is the total number of pixels. Now, under this, if I look at a certain block, a certain smaller block that is arranged in this form again, right? So you have the number of intensities here: 82, 83, 81, 70, 77. There are wide number of values. Now, what are these? These are called the intensities. Now, these intensities represent the color in your image. Now, that color would be a darker or blackish, whiter. So it depends on the type of image. Now type of in the image in the sense that either it is a black and white, is it a grayscale, or it is a color spectrum image. Now, for black and white, the intensities will be generally between the number of bits what is used for each pixel storage. So, if it is generally an 8-bit image, then we will be having the pixels in between 2 power 8, that is 0 to 255. So 0 indicates a black pixel and 255 indicates a white pixel. So like that, the pixel organizations are being framed for generating an visualization of a real-time object. Now, this image is generally a 2D discrete values. Now, this image, how it get generates, how it is stored, depends on the device what we are using for capturing it. So, like if I talk about X-ray images in general, most of we generally we take the X-ray imaging when we have a when we have to analyze the bone structure. Is there any crack, or is there any swelling, or is there any bone tumor or something? Then we have to look out for X-ray imaging. Then we can see that the X-ray images are generally like black and white, mostly like black and white shades. Now, does it mean that it is a black and white? No, it's not a pure black and white image. It's actually a form of color only. It's not even a grayscale image. It's a color image only, represented in the form of RGB. Right. So now that actually generates only in the spectrum. There is no color spectrum in gamma rays. So we have the color shades in the form of a blacks and grays in a combination. Right. Now, but it is having a three different channels, RGB. right? So the one which I'm presenting on the screen, it is simply a 2D image, which is we call in practical as an grayscale image. But when I talk about a color image, generalized images of medical domain, like we can see in the current slide, the medical domain will have lots of data in different formats. Not only imaging, there are different data formats like genomic data, ECG data, radiological data, cardiac catheterization, echocardiogram, blood pressure data, CT scan report, and many. Right. So, like this, we have different forms of medical data. Right. Now, under this medical data, what we have, if we have to do some classification, if we have to do some prediction, and if you have to do any clustering or something, then you need to know the respective properties of that data category, whatever we are using in. So suppose if I try to work on medical imaging domain like radiographical data or CT scan data, then we need to look out or understand how the image is stored in your medical domain and what are the different forms of data storage or data creation in real time. Similarly, if I talk about genomic data, it is like a character set data set, right? There is no nothing about pixel or something. So the entirely data set is different. And similarly, ECG looks like a signal data. Blood pressure is actually again some numerical values which we are trying to predict or which we are going to have as an outputs of blood pressure data analysis, right? So now if I look at this different types of applications in medical domain, every device produces different forms of information and in a different format actually. So now you have different models to train them and different types of models you can use for respective classification. Like ECG classification, you need to use a different model structure. Blood pressure model data classification, you can use a different data models. Genomic data classification, you can use different set of classification models. Similarly, for images we can use different sets of classification models. Now our title is comprising two medical image classification, so we will be talking about what type of medical images we can have, how many ways of formats or you can store, and what are the different types of medical imaging we have in general in today's scenario, and what type of models we can adapt there, right? So now if I look further, this slide presents different types of medical domain itself. I'm not talking about generalized images. Under medical domain itself, we have wide sets of collections of images like x-rays, wherein we get the x-rays of radiography, mammography, fluorescency, and so on. Like this, we have different sets of applications where we can use x-rays. Similarly, ultrasound imaging, which is used for understanding 2D ultrasound, 3D ultrasound, and Doppler ultrasound. So the images are different from X-ray to ultrasound. Similarly, we have CT imaging, which is for angiography and so on. Similarly, the widely adapted or widely research used application is the MRI data and X-ray data, popularly used. These two data sets are widely available over web, wherein many researchers have done lots of work on that depending on the type of disease they are focusing on. So MRI is magnetic resonance imaging, which has MRA, MRP, and fMRP. Like this, under MRI also you have wide sets of collections of imaging. Then we have PET, which is like positron emission tomography. Now, similarly, we have SPECT imaging, which is like single photon emission CT, DSA, OCT, endoscopy, thermography, and digital pathology. Like this, we have different sets of imaging modalities in medical domain itself. In medical domain, right? Now, all these imaging will produce different sorts of information about your same body or organ which we are targeting on to identify some disease or to predict some disease or a daily regular analysis whatever we want to perform. We can use the respective type of modality to do the medical diagnosis on that particular patient. So now, since our topic is more specific to only deep learning models, so I'm not focusing much on the other models. But if I said in one sentence, if I say what all the data we have, either X-ray images or MRI data or PET data or whatever medical imaging we have, for every disease, whatever we are talking of, if any disease is there, disease D. Now, this disease D data set first we need to collect, or we have to find out, or we need to get from the respective hospital. Now, this data will can be used for analysis in three analysis for various applications. One of the application is classification, and another application is prediction, right? Like in classification, you have already a pre-trained model or pre-trained labeled data where you are taking the existing diseases. Already you have a knowledge of with you, and then your now new disease or new patient comes into the hospital, you can classify depending on the symptoms, depending on the feature set, depending on the body organ data, X-ray image or CT image or MRI image. We can classify whether the patient belongs to which type of disease. Then accordingly the diagnosis can be done. Similarly, for predictive analysis also, we can use the same data set and do a predictive analysis. And the similar type of data can be used for clustering as well. matlab, for identifying the groups, similarities of different diseases. Like different diseases might have 80% similar symptoms, but 20% similarities differ between them, right? And there are many diseases wherein you have different symptoms entirely. Like that we can get the data. If we don't know anything about the disease, then we have to look at the internal relationships among the given samples. That means the given data set, whatever is given to us, looking at the images or looking at the pathology report or looking at the clinical report analysis, we can classify them, or you can tag them into the respective disease. So this comes under the unsupervised approach, where we don't have any real information, and then we are trying to identify the among the relationships within the given data itself. Like that, we can use this medical data for clustering, prediction, and classification. Now, when I talk about these data sets in real time for classification, now classification, if I talk about specifically about classification, now classification can be using basically two types of approaches. One is supervised approaches and reinforcement learning approaches, right? Supervised, unsupervised, and reinforcement. Unsupervised completely comes under clustering, so that is why I haven't labeled here. So in classification, you can use supervised approaches where you have already the data, and we can also use certain in advanced sets of applications where you don't know anything about the disease, because you can see that now these days the diseases are growing widely. There are new diseases getting generated where we don't have any labeled data, labeled sample with us, right? So we need to predict based on the new symptoms, new data set what we are getting, new relationships what the patient is going through, what are the new symptoms the patient is going through, to looking at those relationships and the behavior of the patient, how he is behaving, what is the effect due to that new symptom in that human body. By looking at all these real time replications on a human body due to some new disease which is not detected already in earlier, there was no history of such disease, then the learning what we can adapt is the through reinforcement learning models. So where we don't have any prior knowledge about the model, right? So in classification, if I talk about, it is either the full-fledged the labeled data is given to us, then go for supervised. Like if we don't have any labeled information about the new disease, then we have to adapt reinforcement based models for detecting or for classification of new disease. Now, if I talk about this say either the supervised models or reinforcement models. First, let us look at supervised models only. In that, we can use either machine learning models. These supervised models can the data can be supervised. It can be used a machine learning model. Here we can also use a deep learning models, or else we can latest we can say transformer based models, learning based models, right? So under labeled data, we have a different sets of collections of diseases already labeled. We know the symptoms. We have a clinical data. We have a medical data, X-ray image data, let's say CT or whatever the imaging data we have. We have clinical report. We have pathology report. We have a DNA sequence report. Everything we have with respect to one disease of a patient. Now, this whole multimodality data we have, in this we can work either on single modality or we can work on multimodality. So now if I'm in both of this, whether if I'm just targeting on medical images based classification model, then it is called a single modality model. Now under this, if I'm considering a patient's medical image plus the same patient's clinical report, the same patient's pathology report, the same patient DNA sequence report. Suppose like this, if I'm for the same patient X, I'm taking four modalities of data like X-ray and CT scan or something, X-ray, clinical, and pathology report, and followed by the DNA sequence report. Now, if I consider all of them and generating a machine learning model to train it, or I'm generating a deep learning model to train it, or else I can go for transformer based model to train it, right? So like this, I can use three different models on same modality of data for detecting a particular disease Y, or I can consider different modalities of data of same patient and use machine learning, deep learning, or transformer learning model to decide whether the disease is Y or not. Right. So like this, I can adapt similar modality or different modality on three different ways: machine learning, deep learning, and transformer based models. So now if I talk about machine learning models, now these machine learning models already you might be you are already under looking at for from 4 days you are already listening to most of the lectures. By then I think you already knew that what is machine learning and deep learning. Now, machine learning is something like the models, if I name, like SVM, random forest, Bayes, neural network also you can apply, like artificial neural network is also can be adapted in machine learning. Like this, we have a different ADA boost, XG boost, and so on. Like this, we have standard machine learning models. But the prerequisite to use the machine learning models is that you need to have the input ready. That means the features representation must be ready to train your machine learning model. Now, but always it is not mandatory that we will have a trained features with us, like we have a feature set with us. Like if I'm talking about, let's say, the modality of medical imaging like MRI, CT, or PET image or SPECT image or endoscopy image. Now we don't have the features from that image. We just have the images in the form of RGB channel, and the image can be of dicom format, or it can be of PNG format, or the image can be of TIFF format. Like this, we have wide modal different types of image storage. Now from we don't have any numerical values or such features, we don't have any feature set with us, right? So that is why, especially when I'm talking about medical image classification, it is far better to use deep learning models in comparison to machine learning models. Like machine learning models can be adapted where you have already the clinical features extracted for a particular disease. Like for example, if I'm talking about blood pressure data, blood BP measurement values of a particular patient X, patient Y, patient Z. So I have a numerical values interpreted from the blood test or urine test or whatever test we have. We have a numerical values already for the respective patients, right? Now these are the features derived from a test. Now these features are numerical values, and these features have a set of properties to be in disease X, disease Y, or disease Z. So we have a labeled form with respective feature values, labeled set with respective feature values, where we can go for machine learning models. But when I talk about X-ray of a chest, or X-ray of a knee, or MRI of a brain, we don't have any categorization as such directly, because we don't have any features where exactly the tumor is present in MRI, or where exactly the crack is present in X-ray image. So you need to do lots of pre-processing techniques there, and then adapt or identify the respective location where it is. And like this, you need to identify first the numerical feature concept, which is not present with us, but still we need to develop a model which can classify depending on the image. By looking at chest X-ray, it should be able to classify that this patient chest X-ray belongs to pneumonia, let's say one disease. This particular patient chest X-ray belongs to um, um, a COVID, right? Like corona, like something like that, or it is like an pneumonia, or it is like any respiratory issue, right? So that means the image need to be studied, not the features. We don't have any features. The entire image, pixel by pixel, we are supposed to study, and then identify a class, and then identify whether that image belongs to a particular class or not. Now to do this, automatical feature extraction is needed. Like, you need to understand what type of features are present in that particular image, which cannot be done through machine learning models, because machine learning models need features with for it. But for deep learning model has two things inbuilt in it. One is, every deep learning model, if I talk about, every deep learning model will do two things. One is the feature extraction, and then followed by, on these features extracted, it will apply classification, right? So we will extract, we will create, or we will identify the features from that medical X-ray image, and these features are not the proper ones at first stage. So we try to train, or we try to identify the most prominent features which can say that the given X-ray belongs to a disease X, or the given X-ray belongs to disease Y, or it belongs to disease Z, right? So every deep learning model will adapt two basic modules in it. One is feature extraction, then by followed by an classification module. Now these deep learning models are basically derived from one simple concept of learning, that is convolution neural networks, CNNs, or we can also do using vision transformer models, VIT, which is a concept of encoders and decoders. Right. So there are two basic domains where under DL we can either adapt CNN based models, or we can adapt vision based, transformer based models. Now, based on this categories, either it is CNN convolution or transformer. Basically there are two things, either convolution models or transformer based models. So if it is a convolution models, we have n number of DL models again. There are wide sets of CNN standard convolution models. Under them, few of them is like, one of the popularly known model is ResNet, Efficient Net, and so on. Similarly, in VIT also we have wide sets of models. One of them is Swin Transformer, and which works on encoder and decoder concept. Like this, we can have different models in deep learning. One is the CNN, or one is the transformer based models. Now let us look at the basic CNN model. Now, basic CNN model, it takes an input. Now, this CNN basic input is sent to convolution operation. We have here three basic steps. One is convolution, then ReLU activation function is adapted here, then followed by pooling. So there are three basic steps followed in convolution. Now let us look at each one of them for a short. Let's understand how CNN works. Then we'll be looking at what are the standard CNNs and how they differ in properties and how they are adapted in real-time medical imaging, especially medical imaging classification. So now, first, any input, whatever we are taking, the 2D image, the 2D medical image, or 2D image in channels of 3, where we call it as a color image. Right now, these images are sent to convolution filters. So we will be using here convolution layer, we call in general, right? So which generally applies a filter to identify the features now it will apply a convolution layer. It gets the features from the original image. Now these features, whatever are being understood or trained or understood from the given image, will be sent to the max pooling layer. And then max pooling, here it is adapted to max pooling is generally adapted to dimensionality reduction. It is your main purpose here is for dimensionality. It is main purpose is for dimensionality reduction and uh, prominent feature prominent feature extracted, like because it takes okay, let me go one by one. So if I talk about convolution will work something like this. Like every convolution, that means every CNN in general will have a convolution layer, will have a ReLU activation function followed by an pooling layer, and these will be used in combination. This will be used in combination multiple times. Many convolution layers, many ReLU activation function layers, many max pool layers. Combination is done. Like if I take a block, each block contains a convolution, ReLU activation function, and max pooling. If it is this, I'm taking as a pooling. Such blocks, I'll have many which are connected. Once output is given to the other block as an input. Like this, I'll have n number of layers. Convolution, ReLU, pooling. Convolution, ReLU, pooling. Convolution, ReLU, pooling. Convolution, ReLU, pooling. And then we will be sending that to a dense layer here. A dense layer. This dense layer is nothing but it's already known concept to everyone in computer science field, which is an artificial neural network, which is used here specifically for classifying your data to either binary class or the multi-class. Right now, this artificial neural network, what we are talking about, it cannot understand a matrix. Right, ANN is not meant actually for a matrix. This meant it only for a set of values. A set of values, right? That is why the max pooling output, which we are getting as an output of the convolution layers, is generally a 2D matrix. Now, ANN cannot take directly a 2D matrix. It understands only a vector of inputs. So we flatten this data into a one-dimensional array, which we are calling the concept as flatten. Flatten, right? So the 2D feature map, what I'm getting from convolution layers, is converted into a 1D feature map, which is we are calling the concept of flatten. Now this can be sent as an input new artificial neural network, the neurons, can be given as directly to the input to the ANN. Now, this ANN again uses an activation function like either ReLU or sigmoid or TANH. You can actually play with it. You can have a different sets of activation functions here. Then standard activation function what we adapt especially for imaging classification is ReLU activation function, because we need to have the vanishing, we have to remove the vanishing gradient problem. So we adapt here ReLU activation function both in the feature extraction process as well as in the process of classification. Now, after that, this the output of neuron, as we know, artificial neural network, it uses a softmax layer at the end to classify the data into different probabilities in the range of 0 to 1. So it looks at how many multiple classes you have. Depending on that, it will be scaling to different classes, binary class classification problem. Right. So like this, a CNN model works. So if you can observe here the complete figure, the combinations of different convolution, ReLU, pooling, convolution, ReLU, pooling, this can be repeated in multiple ways. Now this is entirely finally generates a simple 2D matrix which we call as a feature map, right, which we call as a feature map. So that means we are actually finding out the features from an image. Now this image can be a medical image or non-medical image, anything, right? Now since it is actually extracting a feature map, this block from here to here can be said as feature extractor. This can be called as an feature extractor. Once the features are ready, you are actually training your model with an artificial neural network. So this is called, we call as an classification module. So in summary, I can say every CNN model holds a feature extractor followed by a classification model, right? So this combines a CNN model as a whole if you summarize it. Now this CNN model, what all it applies, I said it uses convolution, it applies ReLU, it applies pooling. Now what is convolution? If I have a matrix like this, a 6 cross 6 matrix, I'll be working on block by block. So I'll consider a smallest block here. Let's say I take a 3 cross 3 block. Now on this 3 cross 3 block, what is the feature? Is there, do you have a horizontal feature map? Do you have a vertical feature map? Do we have a diagonal feature map? That you can identify through the filters. Now you can have n number of filters here, filter 1, filter 2, filter n, so on, right? Like this we have n filters. Now these filter purpose is to identify what is the prominent feature in that respective block, right? So if I'm talking about image, general image processing, we have only 5 to 6 filters, like 8 directional filters, horizontal, vertical, and with the varied angles, diagonal, right? 8 directions. But if I talk about deep learning, we have to actually extract different sets of features, right? So we have n number of filters in that in our deep learning model. Now, what we are actually doing when I talk about convolution is I take a block by block processing on image, convolution, applying a convolution operator with the filter 1, and same block I'll apply a convolution operator with filter 2, and so on with the filter 3, filter 4, filter 5. Now, what is convolution is? It is a dot product between the block and the filter. That means corresponding pixels multiplication and the whole sum, right? Sum of the corresponding pixels, right? This becomes your convolution operation. Now what is the result of this convolution operation? Now this convolution operation indicates the resultant numerical value what we are getting. This shows whether we, what type of prominent feature we are having in that particular block. Now, how do you know that feature is important or not? That is actually depends on what type of filter you have adapted. So for example, here if I take one filter like this, that which is on the screen, if I take a filter like this, and to take the feature maps, we can use a stride. So suppose if the stride is 1, then we are actually taking a block by block processing, and block by block processing in the sense that we work on the first 3 cross 3 block and we convolve it. So if you simply look at these two examples here, we are considering a block 100, 010, 001 with a dot product of the given filter. So you can see that most of the values will comprise to 0 because we have most zeros here. And if you dot product it, then the value is multiplied here only with the diagonal values will produce to 1. So its summation leads to 3, right? Similarly, if I go to the next block here, the next corresponding 3 cross 3 block, and if I take a convolution operation and take the dot
Sorry to
product.
interrupt you, madam. May I ask one question here?
Yes.
Ma'am, these filter values we create by ourselves, this 1 minus 1, or it is already there? And another question, why these values are only 1 minus 1? Why not
Okay.
other?
Right. So are you gone through any medical imaging, basic image processing? Did you study any course?
Not exactly any course, but I have done some work on brain.
So do you know how an horizontal filter works?
Yes, the filters are applied on a particular block, and by applying the convolution, it getting some edges detected.
Right. So that edges, that value, suppose if I'm taking a filter like 111, 000, like this, if I take such filter, so it is actually, we are actually looking at horizontal filter. Like if there is a horizontal edge in that particular block, the value what is given from the dot product will be high. Otherwise, the value will be low, right? So these values are derived. If I talk about image processing, they are derived by default by different operators. As you asked, why we are taking 111 minus 1 minus 1, it depends on it is like an second order derivative filters concept in the basic image processing. So now second order derivative filters will work on the concepts of differentiation between the values. Now these values are derived with the second order derivative functions, which is already derived by many of the scientists like Prewitt operator, Sobel operator, Canny operator, Krish operator. Like this, we have standard filters already in imaging domain, which comprises the values between 0 to higher value. Some values will be minus also in that. Are you getting it? Right.
Yes,
So
ma'am.
like,
Yes.
right. So these are values which are already standardly defined in, if I talk about basic image processing. But if I'm talking about specifically deep learning model, these values are not uh, given by is not by the जैसे कि we have a convolution operator like canny, right? Convolution edge detection operator, canny operator, it has different values in the filter. Similarly, Sobel has different values. Now these are the not the ones which are using. Now what happens is we take in this a randomly initialized values for these random initialized values. Now we try to train the filter with respect to the image, what exactly the feature map is there in that particular block. That means if you look at this image, see, if you look at this particular image, there is a car object, right? Now the car has trees. In this background you have tree, you have a car, you have a road. Now do we have different edges at different location? Now that one is decided through this filter. Now filter in takes actually like in the form of a 3 cross 3 matrix. Now initially randomly here there will be a random initial values. Now it will check whether the first block is having a horizontal edge or not. If it is doesn't there or it is approximate to horizontal filter, then these values are updated. The weight values in the filter are, we call these as weights. These are updated through backpropagation in CNN models. Through backpropagation in um, backpropagation in CNN models. Right. So if I talk about standard models, then we have a fixed operators for this -1, 0 and all. But if I'm talking about CNN, these values are trained by our deep learning model. Are you getting it?
Yes, ma'am. Thank you. One
Okay.
more question. Why these kernels are mostly, we have seen everywhere that is 3 cross 3. Why not 4 cross 4 or
Right.
6 cross 6?
Yes. If I talk about 6 cross 6, 5 cross 5, 7 cross 7, it will be a larger. One thing is that, and the simplest answer for would be like, I want to extract the most prominent features from the minimum estimated block. Like if I talk about, actually this filter has a beautiful generation. When I have a 3 cross 3 filter, actually I'm identifying the feature map with respect to the center pixel. Is my block with respect to center pixel is towards the horizontal direction, or it is towards the diagonal direction, or it is towards the upper direction, or it is towards the right diagonal, left horizontal, like this. The filter concept works on this 8 directions, which is more prominent and more good enough to identify the relationship of that particular center pixel with the neighboring pixels. This can be betterly, efficiently identified in a 3 cross 3 block. If I go for 4 cross 4 or 5 cross 5, every center pixel has to be analyzed with more number of neighbors, right? So in that case it is not that efficient. But if I talk about 3 cross 3, every center is having a relationship with eight neighboring blocks, pixels. So through which the feature map what gets derived in 3 cross 3 is more good enough for further classification. That is why most of the models, they prefer to be having a filter with of size 3 cross 3. They use 5 cross 5 also, 7 cross 5, 7 cross 7 is a standard one, the larger. They won't use beyond 7 cross 7. Minimum is 3 cross 3 for better efficient feature extraction. Hope I have answered your question.
Yes, ma'am.
Okay.
Thank you so much.
Okay. So like this, we will be working on block by block. And the first block, we got the feature map as 3. And in the second block, we got the feature map as 1. Right. So now here, the stride can be of 1 or the stride can be of 2 also. Like stride 1 in the sense that first we'll be processing this center pixel, as I told you. Then I'm actually processing the next immediate pixel. Then I'm next processing the next pixel, the next pixel, and the next pixel, so on. But if I'm talking about stride 2, then I'm actually processing this pixel, then I'll be processing the next most pixel by skipping the next immediate pixel. So the movement of the block is skipped by one position. And similarly, if the stride is 3, then I'm skipping 2 positions and going to the next block, like this. But we generally fix the stride to be 1 because we want to extract the most prominent features from the entire image, which can be done only when you want to process, when we will process every pixel by pixel, right? That is why we will not skip such positions. We will extract the feature map with respect to one, what is the feature map in this direction, what is the feature map in this direction, what is the feature map with respect to all the directions for every pixel. So we try to fix the stride to be as one in most of the standard CNN architectures. We will not go for stride as 2. So like this, we move on the stride and find out the feature maps. So like we and process the entire given 6 cross 6 image. So you can see here the picture map is derived here, which is again a 2D matrix, but the size got reduced here to 4 cross 4. We had an image size of 6 cross 6, but the output is 4 cross 4. This is because, as I told you, the feature filter works with respect to center. That means first we are actually processing this pixel with this pixel, what is with respect to this pixel, what is the orientation of its edge, right? Then I followed this, then we followed this, then we followed this, so on up to this position. That means I have looked into the relationships of these pixels alone only. That is why we got a matrix size feature map of size 4 cross 4, not a 6 cross 6, right? But in general, we have to get the feature map of size 6 cross 6, not 4 cross 4. So for that, that means I need to look at this position also with respect to these angles, right? And similarly, this corner pixel also with respect to the three orientations, right? So this I have skipped right now, the ones which I'm getting a feature map over in this place, right? So to generally CNN does like this, and it avoids the corner pixels because the center concept is adapted here. Now I want to have the feature maps with respect to corner pixels also. That is why we do a concept called in convolution called as padding, which means I add an extra row here on all sides to extract the feature maps of the corner pixels as well. Now, padding can be zero padding, and the padding can be duplication padding. So we adapt a padding concept to extract the features of all the pixels. So when I do padding with zero, the feature map size will be 6 cross 6. That means for every pixel in the original image, I have extracted the feature map. Like the values we got here, 3, -1, 0, -2, and so on. Like this, I can extract all the feature maps of the given image. So always apply padding whenever you do a convolution based feature extraction. Now, like this, will be doing multiple filters. Here we have shown only one filter. Like this, we have multiple filters. Now, as we have a multiple filters, obviously I will get multiple feature maps like this. So if you have 50 filters, you will get 50 feature maps. If you have 100 filters, you will have 100 feature maps, right? Now, again, this feature map size is again, as I told you, if the padding size, if I add, the feature map size is again going to be a 6 cross 6, right? So in this example, in real time, we will have the generalized images of medical domain. If I talk about specifically, it will be around 20,000 2000 cross 2000, or 8,000 to 1,500 into 1,800, something like that. Like that, we will have the size of the medical image, right? And that medical image into three channels, RGB, so you can understand what is the complexity of that image representation, right? So if I process the filters on this particular entire representation of the image, obviously the feature map is also again of same size, 2000 into 3000 into 3, right? Now this further processing again into the next convolution, again into the next convolution, as it is shown in this particular run. As you can see, convolution relu, max polling, convolution relu, polling, convolution relu, polling, so on. Then finally we flatten it, right? So when I go for combination, repeated the combination, obviously your feature map, if it is of size larger, it will take too much of time, right? So that is why the pooling tries to help to extract prominent features and reduce the dimensionality, to extract the prominent features and reduce the dimensionality of your feature map. So that is why here we apply a two stride. Now what is a back pooling is, like suppose if you have an image like this, then I'll be taking a 2 cross 2 block at every interval and take the maximum of this. Right. So suppose if my image is 200 cross 200, I will be moving on every non-overlapping blocks. That means I have processed to first 2 cross 2 block, then I will process the next 2 cross 2 block, then again I'll process the next 2 cross 2 block, like this. Right. So my image of 200 cross 200, it will now reduce to 100 cross 100 because of this pooling, max pooling. You can apply here min pooling, you can apply max pooling, you can apply average pooling. In practice, we apply max pooling for better results, right? So like this, we can reduce the dimensionality of the image, and then further we can go for further feature extraction of that image. And finally, the features what we are getting after the feature extraction, that will be like the matrix what get generated as an output of this last layer will be holding the most prominent features which can derive our car, the input as it is shown here. Right. So now those are most prominent features which can describe car efficiently. Then those features can be further used for dense layers to classify the model. Right. So like this, the CNN works. Now this CNN um, can be adapted in wide variety of architectures. One of the standard architecture is VGG. You can see here, these two are convolution layers. Then we have a max pool layer, then again two convolution, then again a max pool, then again three convolutions, then again a max pool, then again three convolutions, then again a max pool, then again three convolutions and again an max pool. And after this, we are actually here doing a flatten. Now, after flatten, we are sending to fully connected layers. FV stands here for fully connected layers, and this further classifies into number of classes. So this, from here to here, it is feature extraction. From here to here, it is feature classification. Right. So this is how a generalized CNN model works. Now, if I'm taking this particular pattern flow, then it is called as an VGG standard architecture model. Like this, we have n number of architectures. Now, this VGG model will hold will hold around these many number of parameters. Now, what are parameters? These are called trainable parameters to train your model. Now, every VGG architecture, what I'm showing here, every CNN architecture will depend on the complexity of the model. As we already know in general, like if I have to say this model is efficient, we'll be looking at two things. What is the time complexity? What is the space complexity? So similarly, for this architectures also, we will be looking at how many trainable parameters are there, because on which only your time depends and your efficiency depends. So trainable parameters should be less. It cannot be large. If how many, depending on number of trainable parameters, the model becomes too complex. Right. Now, these parameters can be identified with a one standard formula, which is a filter height, filter width, number of channels, number of filters, plus the biases, because every filter will have a one bias. Right. So using this formula, we can find out how many parameters every layer can take. Now, if I calculate all such parameters for VGG architecture for every layer by layer, then finally I'll be getting around 138,357,544 number of parameters. Now, if I compare all the standard CNN models, we have some standard model called LeNet, which takes around 60K parameters, AlexNet, which takes around 61 parameters, VGG 16 takes 138 million parameters, VGG 19 takes 144 million parameters. Similarly, ResNet 152, that means how many layers are we taking, is 152 number of layers, which takes around 60.2 million parameters. Right. Like that, inception takes 55 million parameters. We have one standard architecture of CNN, which is called dense net, exception net, mobile net, and so on. So all these are based on base concept of CNN, feature extractor and classifier, and base concept adapted here is a convolution layer, convolution based feature extractor. Now, if you can observe here, the mobile net is taking very less number of parameters, like only 4 million, 3 million, 5 million. What is the need of this? Why should I don't use the higher dense models? Because if you look at DenseNet 264, it is very deep neural network. It can extract more prominent features compared to mobile net. But in real time, do I have to go for a standard with more number of layers or a standard with less number of neurons? Depends on the application exactly. Like if I'm trying to update deploy this classification model on small sensor device like a camera, then if this camera is already having low memory device, it's like a memory constrained device, right? So if I deploy a DenseNet 264, it cannot be handled with some small IoT device, because it needs high processing time and high processing memory, so which cannot be handled with smaller devices. So every smaller device should hold architecture for classification, but with less number of parameters. So mobile net would be a suitable one to give you the efficient classification with minimal number of parameters, and it is adaptable to any type of medical device, any device actually, not medical, any device. Now in medical domain, we need faster results. Within fraction of seconds we want to have a prediction, because if I take even a fraction of second delay in identifying the patient behavior, then there could be some big mishappening to the patient, right? So I have to handle in few seconds. But that monitoring should be done continuously, right? So we have to use or deploy the models which are in lightweight with respect to parameters, and it should be also efficient to extract the most prominent feature maps from that particular patient. That is why we look at the lightweight models with better efficiency in medical domain, and also adaptable to the real time. Not only the simple small lightweight, but it is not suitable for a particular disease, then there is no use. So you have to look at multiple constraints. So regarding this, we have certain applications already developed using deep learning for medical image classification. Well, few publications few of my students have already done. Let me show up them. So one of their such application is an ensemble model to detect COVID-19 and pneumonia using chest X-ray images. So here we have actually using chest X-ray of a patient. So like this, in this architecture, you can see we have the chest X-ray of a patient indicating the pneumonia, indicating the images of normal patient, and from the COVID patient, we have a three collections of chest X-ray images. Now we have ensembled model used here. One is the efficient network and the mobile network. So these images are passed through efficient net CNN model, mobile net CNN model. Whatever the feature flatten data, 1D feature map, whatever it is generating, 1D feature map, whatever it is generating, we have concatenated here and then used a set of fully connected layers for, like this, set of fully connected layers for classification to COVID, normal, and pneumonia. So you can see here in the last table also the set of accuracies for class wise accuracy. So we can see that COVID-19 is having around 98% accuracy, pneumonia 95% accuracy, and normal we got around 89% accuracy. So this is the model which is for chest X-ray classification using ensemble model. Similarly, we have another paper which is used for um, bleeding and non-bleeding endoscopy image classification, wherein we adapted a mobile net architecture, the standard CNN architecture, which is named as mobile net. And since here, if I look at specifically about the medical domain called wireless capsule endoscopy image, here the images are something like this. Like we take the endoscopy images where the images might look like this in the form of A or B. A is a category of endoscopy images with the blood floating, and the B is now non-blood floating. So if there is a heavy blood floating, then immediate action need to be taken on the patient. And if there is no blood floating, then we can actually relax here. So immediate action need to be taken here, so that here for this particular classification we have adapted an model called as mobile net followed with the color, because we have a dominance of red color. If you look at the sample images in A, the red dominance is more, but in the sample of B there is no much dominance of red. So red component is playing a wider role in classifying these two category of images. So we adapted a model to extract the color histogram, and also adapted the features of the both the images, whether it is bleeding or non-bleeding, through mobile net by processing block by block as a convolution layer model. Now then after that we have flattened them and concatenated both the features. Then we applied a set of dense layers, which is simply an artificial neural network, and we applied a softmax function over here to classify bleeding and non-bleeding, right? So this is one such application. Another domain is different. So I have shown you two different domains where the CNN are being adapted. One is X-ray image classification, another one is endoscopy image classification. Similarly, we have adapted here another combination of uh, ensemble model for classifying the COVID-19 image with the non-COVID-19 images, again using the same chest ray X-ray images. Here the modality, here the mobile net is adapted again with an enriched features classification here. So here we adapted the basic pre-processing. One is the standardization, augmentation and all. Then we have extracted the features using CGAN. Then we applied a modified mobile net approach, and then we applied recurrent neural network for classifying the into three categories by finding out the um, count score, actually moderate, severe or critical. Like this we adapted one paper in the field of same medical image domain with adapting various sets of CNN models. So these are the different accuracies of that respective paper. So you can see there is a higher accuracy for the proposed model. Similarly, there is another paper here which is also adapted with the same X-ray image classification, COVID, COVID and non-COVID. So again, here we adapted an custom CNN model, a deep neural network we have developed by our own, which have named it as an SRC2. So we adapted or we created our own CNN architecture. Our main target in this paper was to reduce the number of features and give the same accuracy as the standard architectures, which are having high parameters and giving the same accuracy. We adapted a small CNN model with less number of parameters and proved that the accuracy is going to be the same. Similar accuracy we can obtain with a lesser weighted, lightweight model of custom CNN. So with this, we have found the accuracy also. So you can see the proposed model had only these number of parameters, but the existing models had very high number of parameters. And we tried and we achieved an accuracy of 98% all with our own feature extractor model and our own classification model, respectively. So like this, we adapted most of the deep learning models in real time to adapt the classification in with better accuracy. Now, but even then, though the accuracy is high with the deep learning models, there are certain challenges left out in deep learning models as well. That is data set requirement. If I look at the second point here, deep learning models requires large labeled data sets for training. That means you need to have huge data set for training the model, right? And accuracy is always high accuracy is obtained because you have a large data sets, right? But in real time, do we get really such large data sets specifically in medical domain? is not guaranteed, because in medical domain, particular diseases, let's say cancer, right? So cancer also have different types of cancer. Now some types of cancers are very rare, where you don't have huge sets of samples, you have only samples in the form of sets of hundreds, and other cancers data sets are in millions. Now how can you train a model wherein you have only less number of samples with a comparatively analysis of other cancers which are of very high, right? So a model will be biased if I train the data set directly like that, even with a deep learning. And deep learning is a requirement that the data set should be high, right? And the due to which the problems gets into encountered, like data imbalance, and adversarial attacks can happen like that. We have lots of challenges here. Now to overcome these challenges, if I summarize the challenges, that is, one is the requirement of larger data sets, data imbalance, and everything is black box. Nobody knows what is happening in the deep learning, though we know the architecture layer by layer structure, but how exactly, I told you how the neuron is updating, how backpropagation is used, all these things, how the values are updated, how the model is trained, this nobody knows exactly. You know the concept, but what exactly the value is there in after weight updation, this we cannot know, right? So this is very high computationally costly. So that is why we try to go for the next future in classification models, which is quantum based machine learning models, like QML, you can say quantum machine learning, right? Now why quantum machine learning? To speed up, it is, you can do the parallel processing in quantum processing. So that means the advantages is, one is the high dimensional data can be understood here, you can do huge parallelism, and you can have the quantum inspired neural, you have to use the quantum inspired neural networks obviously, but it will give you the better efficiency if they are developed in future. Right now there are very limited quantum machines available, due to which we are facing the hardware challenges as well as the software challenges. But in near future, like in within 5 to 6 years, I hope that we might get a better quantum model which can be deployed in our servers, and we can use it for our local machine. I hope this will happen in next to 5 to 6 years, right? So let us look into what exactly in the quantum we have done. One of my PhD scholars thesis was going on this, and he adapted. We try to adapt the class quantum machine learning model for feature extraction or for the classification. So we looked at both the cases. For feature extraction, we have used quantum machine learning model, and for classification also we have used the quantum machine learning model. Now, under this, we have some relevant architectures. Because the time is less, I would like to go through the main concept. So, we have published one paper here, which is a hybrid framework for respiratory lung disease detection based on classification CNN and quantum classifiers from chest X-ray. Now, same data set we have used for used in classical models also, like we have adapted the data. Custom CNN we have used on the same data set, and we have used the ResNet model on the same data set. We have used MobileNet on the same data set. Now we have used the quantum machine models also on the same data set. Now under quantum machine learning models, you can see in this architecture module 1 and module 2. Under module 1, which is a feature extraction, wherein we applied a custom CNN, like existing CNN feature extractor we have used, model based custom CNN we have designed here, and then we followed with an classification model under quantum. So we have converted this feature extracted, which is flattened data from the feature extractor. We transform them into qubits, which is required for quantum processor. Now these qubits, we have an encoder there. We have used the quantum classifier MMS and MSMS. We have designed two different classifiers here due to, and then we followed with the softmax. We classified into the pneumonia and the non-pneumonia, cancer and sorry, COVID and non-COVID. So, like this, we have adapted the quantum classification. The model can be said as an for feature extracted, we used custom CNN. For classification, we adapted quantum classifier. So it is like classical and quantum hybrid model. So with this, we had a better efficient accuracy, which is about, if you can see in this figure, we can see that CCML MMS and CCMSMS, we can see the accuracy for here it is around about 98%, right? Then again, we have another paper here where we have reversed the concept, hybrid QCC. Under in this, we have done a hybrid framework for automated respiratory disease based on quantum feature extractor and custom classifier. We have reversed the process. So first, we applied here quantum machine learning for feature extraction, and for classification, we adapted the custom classifier like dense layers, artificial neural network classifier. So here the feature extraction is done through quantums, and once a quantum has given our feature map, those are converted back to the from qubits, it has been converted back to a numerical value. Then we applied to the custom classifier. Now with this, again, we have a good enough accuracy again. So you can see here with the q depth 4 matlab the qubit 4. If we have a qubit representation, that I will take another lecture if it is possible in future develop FDPs or so on. So I can explain there what is exactly the quantum qubit and so on. So if we have used here quantum 4, we got the accuracy to be as 86, 97, and 88 respectively. And if we have used quantum 6, we got the accuracy about 87, 97, and 88.9 respectively, with respect to F scores and precision, sensitivity, accuracy, and so on. Similarly, if the same data set is been adapted with normal mobile net, VGG, ResNet, and so on, this is the trainable parameters. You can see the parameters are many for classification models, but if I am talking about the parameters in quantum machine model, the parameters are less. And the training accuracy is almost the same. I won't say we have got the best accuracy, but we got the similar accuracy like in classification models, but the processing time, the parameters were less here in compared to deep convolution neural network. This is another comparison with the literature. We had a 41 reference and so on with the various standard deep learning models again. So we have seen the different ways here, the different feature extractors, like we adapted ResNet for feature extraction and proposing our own classification model, and custom classification for feature extraction, and we adapted one quantum machine learning model. With that also, we tried to we got a better accuracy in comparison to the standalone approaches. So you can see here with the custom, our own custom model for feature extraction and our own classification model of quantum, we reached accuracy about 96%. And in the standard deep learning models also, we have a similar accuracy. I won't say that we have bypassed the accuracy, but we got a similar accuracy even with the quantum based models. So in future, we can adapt quantum lane based models with if case the hardware is available to everyone, and if the price gets reduced, the usability prices gets reduced, we can adapt them and we can do the even more better efficient classification with less number of samples as well, which is the main drawback in the deep neural networks. We need to have large sets of data sets, huge sets of data sets for a particular medical image domain classification model. We can restrict it and we can adapt quantum machine learning models as well. So this is a overview of how what is a CNN, what is a medical image domain, and what are the types of medical images, and what are the models we can have in standard deep convolution neural networks, and what are the limitations of it, how they can be used for better efficient calculation of efficient classification of medical image domain. And then we can use the next future we can try to use for cloud based quantum machine learning models. And then we can go for regulatory considerations in future health AI and so on. So this is what I have discussed today. What is the basic of CNN, then followed by standard architectures, the drawbacks, and then how they can be adapted in real time, and then how quantum are able to give better accuracies as compatible to the standard deep neural networks. Thank you, sir.
Hello, ma'am, please share your
Yes.
email ID.
Yeah, sure. I think on the first slide I have my email ID. Yes. It's rajita at mnnit.ac.in.
Any queries?
Any questions from the participants?
Is there any queries?
Ma'am, meeting alert is showing. Can you please share the first slide? First slide.
First slide. Yeah.
Okay. Ma'am, please hold this for a moment. I will note down.
Okay.
I think there is no queries anymore.
Thank you, ma'am. Session was very very interesting and nice. And you started from basic concept and then you went towards your paper. So basically, quantum computing and all these things are now very new nowadays. So if we could do this kind, I'm working, ma'am, uh, in my lung diseases, and
Okay.
I am using the CNN. But this novel idea we can use as you suggested, quantum computing, and I will contact you about your work.
Yeah, sure. I'm available on internet. Like through email, you can contact me, or through on my phone also you can contact me. We can have a discussion on it later.
Okay, ma'am. Thank you so much once again.
Okay. Okay. Okay, sir. Then I hope
Okay,
I
ma'am.
can leave.